it used to be like speakers from the UAE universities in general, like within the sessions, but this is the first time to have a standalone session, and it's my pleasure to be the chair of this first session. Thank you, Tony, for the invitation. And it's my pleasure to introduce our first speaker, Dr. Mohamed Qenawy. He's an assistant professor of chemistry at the Department of Chemistry, UAE University. He is also a member of the steering committee member of the Arab-German Young Academy. He got his PhD in 2016 from Lund University. His research mainly is on lasers and nanomaterials and laser spectroscopy. The floor is yours.
Okay, thank you so much. It is really my great pleasure to stand here now in front of you, and I would like to thank Dr. Yasser for this nice introduction, Professor Tony for the kind invitation, and also to be among such great scientists. And yeah, so my name is Mohamed Abdellah and Qenawy, and actually I am going to tell you now how laser spectroscopy or ultra-fast spectroscopy can be a very powerful tool in order if you would like really to characterize, optimize, enhance any light-matter interaction for any kind of application, as I will tell you. So this is the outline of my talk. I will be talking about first just giving you a brief about myself. Then we will talk about mainly used or mainly studied materials as well as my powerful technique I'm using. And I will end up my talk by conclusion and acknowledgement. Who am I? Mohamed Qenawy. Very clear. I'm from Egypt. And I am from the south part of Egypt, very, very south, Upper Egypt. And it is a city called Qenawy, which is really between Red Sea and Luxor, which is a very ancient city. Then I moved to Greece, University of Ioannina, where I did my master in making novel materials for cancer treatment. After that, I went to one of the coldest parts over the planet, which is my lovely Sweden, where I did my PhD at Lund University, 2016. I finished, then I moved to Uppsala University, a little bit in the north, where I did 2 postdoc, and I moved to United Arab Emirates University beginning of 2023, and you can imagine from minus 13, 14 in Sweden to 25 in Al Ain, that was a little bit big change. So, and actually I would like to just echo what Antonio Guterres mentioned less than a year ago, and when he said that the global warming has ended, but the global boiling has started, which is really not good news, because actually we already booked our seat, our hot seat, because July 2023 was the hottest month recorded ever, and the entire planet is disaster. The only surprise, how fast we are moving in the climate change. And again, it is just the beginning. So the air is not breathable and the heat is unbearable. We don't have time. We need to take actions for that. But there is hope if we tried our best to minimize the growth in the temperature around or less than 1.5 degrees. So energy. One of the reasons that our planet is boiling actually is how we consume energy, how we produce energy. And energy campus, how I call it, it controls everything around our daily life. It controls our economy, our society, nature around us, and of course, the world peace. And of course, we have many examples on that. But do we have other alternatives for energy? Of course we have. Solar energy. Solar energy is a beautiful energy, free energy, clean energy, permanent energy. And believe me, if we manage to utilize it in an efficient way, then it can be more than our demands. So my interest actually starts how we can harvest solar energy, especially in countries like Emirates here, we have sun always. So it is really great if we can invest in such making materials, smart materials, interact with the light in order to produce charges. These charges can be used for any kind of application, as I will tell you. So what I used during my last 10 years, 11 years actually, I study different materials. All of them are light actives, which means that they interact with the light, such as quantum dots, such as perovskite materials, plasmonic materials. This, I use them in order to make a solar cell where we can simply convert solar energy to electricity or into electricity. For solar foil production, where you can produce something like hydrogen, you can reduce CO2, so you can produce some chemical with energy value. I use semiconductor-based systems, molecular assemblies, and polydots. And recently, I am very interested in COF and MOF. And of course, yesterday, actually, we had a great talks from a great scientist working in COF and MOF, and this is opening a new doors, actually, for us to use such amazing materials. So, when it comes to techniques, I work with laser spectroscopy techniques, which means that I try to use the light or the ultra-fast laser pulses in order to understand, because the reaction of light with any matter, it's very fast. It's 50-second time scale. In that kind of time order, you need to use something even faster. That's why I got interested in using different techniques, one called transient absorption spectroscopy, the other one time resolved spectroscopy, where you use ultra-fast light pulses to see the interaction between the light and the matter. As well as I am part of a big team that we are also interested in how the light can actually change the crystal structure. And for that, you need to use X-ray or synchrotron-based X-ray. So I am part of a team that we visited almost all the free electron laser all over the world, like, for example, MAX4 in Sweden, ABS in the States, DISE and EU XFL in Hamburg in Germany, SACLA in Japan, and Surrey in France. Where there, you can even look at how the crystal change as a function of light, a light interaction. So, 2023, actually, it was actually my year that I celebrated the Nobel Prize with these people. Because why? First one, in chemistry, it was given to this great scientist who, for their discovery and synthesis of quantum dots, where I did my PhD in quantum dots. So that's for me like was a prize. And I used to read all these people papers. And at the same year, actually, in physics, it was given for ultra-fast laser spectroscopy, attosecond. And one of the laureates for Nobel Prize, Professor Anna Horier, which is from Sweden, from my Lund, actually, from my university at the time. And actually, we used to share the same lab at some point. So let's go back now. Time-resolved spectroscopy, actually, it was developed in 18th by Professor Ahmed Zuhail. And of course, he got Nobel Prize in 1999 when he tried to understand how light interact with the matter. And how it works, it's very simple technique, very simple technique. You have your light-active material, you bump it, excite it, hammer it with high-energy photon, but with short pulse, very short pulse, 150 seconds maybe. And then, after a certain delay, you send another light. This light will probe, will check how the absorption change, and since you have delay between bump and probe, you can put time domain. You can look at how that absorption change as function of time. And this is how it works. So you send the bump, you send the probe, and then you measure that, what we call it the differential spectroscopy between them, as I will let you know in a while. So, again, pump at the probe, and based on your probe light, you can look at the properties of your material. For example, if your material interacts with the light in the visible range, you send the probe with white light. If it's in the IR, vibrational mode, you send an IR pulse. If you are in X-ray, you send a bunch of X-ray. If you are looking only for the recombination of charges, you just look at the time-resolved photoluminescence spectroscopy. And this is how the laser labs I work with looks like from inside. Of course, looks really pretty, but when it comes to a real measurement, it is so hard. Because you need to start from the laser at the beginning until you catch your sample, and you need to do all this kind of alignment. So this technique actually is very powerful, and it, for me at least, I have learned from this technique what is the challenges, what is the bottlenecks we need to overcome in order to have efficient solar harvesting system, as I will tell you in a while. So if you look at the absorption of the sample that bumped, the sample is unbumped, they look identical. You don't see anything different. But actually, all the fun and all the interesting information start to show up when you just subtract the unbumped from bumped. And you get what we call it the TA, transient absorption difference spectrum, where you can see how your signal get bleached, how new signals can be absorbed, and even how the emission looks like. and this is how it looks like. For example, when you excite your sample by the pump, so your sample will not absorb any light in this particular point when you probe. That's why you get what we call it bleach, negative signal. Then, if you have new species that formed during the reaction with the light, and they make a new species, they will absorb in different wavelengths. So you absorb more light. And if some of the samples or some of the excited sample recombine, you will get what we call it simultaneous emission. And this now reported spectra at different delay time, at different time. So you are seeing the progress of your spectra as a function of time. Then if you take slices at certain wavelengths, and you want to see how this prograde with the time, as function of time, you get what we call it the time traces. So you fix wavelengths, and you look at the species, and you see how they prograde or bleached as function of time. During my work in Lund University, actually, I was very interested in the solar energy. And this is a very simple scheme, how solar cell works. Simply, you would like to have your light-active material in a sandwich structure between electron acceptor and hole acceptor. And your task is very easy. You want to excite this light-active material, you want to get the charges out, and you need these two charges to move outside of the light-active material in the same time with the same efficiency. If you don't catch this condition, you will have not very efficient solar cell device. And for that, I was lucky because I work with many groups, very active groups, and you managed to study so many different materials. We study perovskite, different structure, nanowires, quantum dot of perovskite, cadmium cyanide quantum dot. We study what else? Plasmonic material. And we measure all of that using ultra-fast laser spectroscopy, and we get our conclusion, which I will end up my talk with. So, as an example, quantum dots. What are quantum dots? They are semiconductor nanomaterials. They have a size between 2 to 10 to 8 nanometer in size, so they have the quantum confinement. What does it mean? You have the charges are confined within the crystal structure. So they are beautiful when it comes to absorption. They can be kind of easy to be done or to be prepared in the lab, and they have beautiful and tunable optical activity. As you look here now, that's why they have plenty of application. In vivo imaging and diagnosis, LEDs. And if you look here now, all of these colors, believe it, same chemistry, but totally different physics. Why? Based on the way you cook your quantum dot, you get different size, different band gap. Based on the band gap, you can determine how they can absorb the light. If you have different band gaps, you will have different light to be absorbed. So here, different physics, but same chemistry. In normal life, that's how quantum dot looks like. Thousands of atoms arranged in a certain beautiful way. But once they interact with the light, you create excitons. These excitons will relax quickly to the conduction band minimum and valence band maximum. And at some point, if it's ideal, within 20, 30, 40 nanoseconds, they will recombine, giving light. This is ideal case, which is not always the case. So what happens if we have some trap states? And these trap states work as a hunter for the charges. They can be deep, they can be shallow. So in case of having trap states, electron or hole or both can be trapped sometime. And if they are trapped, imagine now, you cannot take the charge outside. So this is limiting for the solar cell efficiency. So, and then they can recombine later from different wavelengths. So service playing an important role there. How the sample is passivated is very important because this can easily affect the exciton dynamics. It can quench the quantum yield, and it can hinder the charge transport. So this is something very important. That's why we came with the idea, can we passivate the service? And we were not the first people to do that, actually, because there are different approaches. This is the just core quantum dot. This is core shell, step 1, step-like core shell, type 1, and reverse type 1. So here, depend on the band gap of the core and the shell, you can design either type 1 or reverse type 1. And what we made new at this time, we make what we call it the gradient core shell quantum dot, which means that the change from the core materials to the shell materials, smooth. So you don't create any interfacial trap states. And we managed to study the charge dynamics, the electron dynamics, hole dynamics, as well as how this kind of dynamics affect the performance in solar cell. All that done by ultra-fast laser spectroscopy techniques. How we did that? We grow our core, and then we grow the shell. And the shell, when I mean shell, it's like onion shells. layer after layer. We grow that, and we confirm our shell thickness using high-resolution TEM, and of course with some similar characterization. And this is my samples, how they look like under UV light. So they are very beautiful. And this is now the laser spectroscopy I told you before. This we call it spectral traces. Why? Because if you see here, we have different times. At certain time, you snap. You take a capture of how a spectra looks like. And what happens now here? It's negative charge, means it's bleaching. What does it mean? It means simply that by excitation, all the electrons, or some of the electrons, moved from the valence band to the conduction band. And then when the probe comes at certain delay, you will see that the bleaching getting recovered, which means that the electrons start to return back to the valence band. And then what we did, we just compare the time traces as the bleaching recovery here for our quantum dots, just core and different shell thicknesses. Once we introduce material can take the electrons. Electrons can inject it to these materials, which in that case we use zinc oxide. So what happens, if you look now, compare, you will see that the black one just show you how the red one, the red lines show you how the quantum dots behave alone. Compared to the black one's lines, they show you how the quantum dot behave on zinc oxide. And if you compare easily, you'll find there is faster bleach recovery, which means that electrons are transmitted now from the quantum dot into the zinc oxide conduction band. And of course, there is a dependence on the shell thickness. What shell thickness? Which is the optimal, or the distance from the quantum dot to zinc oxide, which is the shell thickness. And when we compare the injection efficiency of electrons from the core via the shell to zinc oxide as a function of the quantum yield, what is quantum yield? Quantum yield simply reflecting how qualified is your sample. Is there any trap states or not? And you see that we got what we call it optimal distance, which is around 1 nanometer, where within this shell thickness, the quantum dots are well passivated. Awesome. What else? The electron efficiency, injection efficiency, is still very high, almost 80%. So by that, we found that compared to step-like, our materials show larger dependence on the shell, but that makes sense, because in a step-like, only widths change as you move from core to the shell. But in the gradient 1 hours, both widths and height, widths and height, widths and height. That's why we show larger dependence, but we're still passivating our quantum dot in a good way with high injection efficiency. Then, of course, quantum dot was there, but perovskite just show in the media around 2012. And actually, we were the first to start to study the charge dynamics, because perovskite, when it starts to show its activity in solar cells, it starts very high. But no one knows why. But by kind of spectroscopy techniques like photoluminescence, transient absorption, terahertz, microwave conductivity, we find that such materials are beautiful because, first, once you create the extons, which is electron hole pair, immediately within 2 picoseconds, they became free charge to move. Not only that, they are highly mobile. They can transfer long distances. They have lifetime up to microsecond. Microsecond, it's a very long time in ultra-fast. And of course, both electron and hole, they move more or less with the same speed, which we need as well for efficient solar cell performance. Then, during my time in Uppsala University, actually, I work in Angstrom Laboratory, which is a well-known and new facility. Not new. This building is new, but the facility is there for I think, for maybe 20 or 25 years now. So this is, again, how photocatalysis system works. So now we talk about solar cell, how it works. Let's talk about photocatalysis. Both are solar energy harvesting. So I focus mainly on this part, where our light absorber interact with the light, produces charges to the acceptor, to the catalysis, and then based on the catalysis, you can do hydrogen evolution, you can do CO2 reduction. And for that, we also study so many systems. And we have published very good papers, actually, with other collaborators for water splitting, for CO2 reduction. And I will take you now in about this one. So what happened here, actually? That was in a collaboration with Professor Erwan Reisner. At the time, he was in Cambridge University. And what we find, he prepared such a beautiful catalyst based on biprodiol, this rhenium catalyst. And he asked me, we have this sample now, and it's work with high efficiency for CO2 photo reduction only on titanium dioxide? Question mark. Why? Because if you think about that, this catalyst, first, it's play Dow rule. What Dow rule? It works as light absorber, interact with the light, and at the same point, at the same time, it gets activated to reduce CO2 to CO selectively. Because this catalyst is not really new catalyst. It's old one. It's like, I think, since 1982. So it is really old catalyst. So what they found, he asked me, can you help me? What is going on? And by taking his catalyst, just very simple comparison, the catalyst on zirconium oxide compared to the catalyst on titanium dioxide, same catalyst, exactly the same. But we got different spectroscopy. And this kind of different spectroscopy tells us a lot, or told us a lot. Why? If you look carefully here, what difference between zirconium oxide and titanium dioxide? Zirconium oxide is a wide band gap semiconductors. So there is no charge can be injected from the catalyst to titanium dioxide, to zirconium oxide. On the other hand, titanium dioxide is not wide band gap. So if there is a charge in the catalyst itself, they can be injected to the titanium dioxide. And they look similar, except, first, the offset. And here we are in the IR, near IR region, mid-IR range, right? So we have the offset. This tells us something, I will tell you now. Plus, this beautiful, tiny, new feature, which is not here. So we have only the bleaching, but we have this one and this one. This one in the IR actually tells you that there is free electrons in titanium dioxide conduction band. Free electrons. While this beautiful small new band here, or peak here, this tells us there is a new features, there is a new species has been formed. And the only way to see that, if the catalyst itself injecting electrons to the titanium dioxide. And that was the case. We confirmed that. And even when we went up to 10 microseconds, we still see charge in the conduction band of titanium dioxide. So that was a little bit confusing, because this catalyst need to be reduced in order to reduce CO2. But in that case, it became oxidized. And by too many experiments in presence and without what we call it the sacrificial donor, we confirmed that how the mechanism looks like. So it was really too much work. I don't want to take you in this very deep details. But what we find actually that up to second time scale, the catalyst and the titanium dioxide playing a ping-pong rule, ping-pong game, where happen after excitation of the catalyst inject electrons to titanium dioxide. And since titanium dioxide contains many trap states, surface trap states, it works as electron container. And it keeps the electrons until the catalyst itself rearrange the environment, getting ready, and then within second time scale, the titanium dioxide electron go back to the catalyst to make the reduction of CO2 to CO. And that's why I answer him, titanium dioxide, not only scaffold, has electronic interaction with the catalyst. And that was the proposed mechanism he proposed before making spectroscopy. And this one, what we figure out. So we managed to see signature of each intermediate for such catalyst. Then I think we will go also talk about the competitive Hall charge transfer. So this is another system where we have nickel oxide and we have quantum dot again with catalyst. And what happened here, based on the published paper, actually, the author, my one from Dalian University in China, she told me that we have the quantum dot, and we believe there is a charge injection from the quantum dot to the catalyst, and also from the quantum dot, the holes can be to nickel oxide. Nickel oxide is p-type semiconductor. It accepts holes. But we don't know why we have low efficiency. And by doing a lot of spectroscopy as well in the visible range, we confirm the electron hopping by comparing the bleaching recovery when you have just the quantum dot on nickel oxide and the quantum dot on nickel oxide with the catalyst. This kind of difference tells us there is electron hopping from the quantum dot to the cobalt oxime. What about the holes? We figure out that this spectroscopy looks very weird from what I get for cadmium selenide. And simply because she used a lot of sulfide as a capping agent. This extra sulfide getting the holes and form what we call it the polysulfide radicals, which is totally irreversible process. Once they form it, they're still there. That's why they absorb in the entire. So we talk, and I told her, unfortunately, by exciting the quantum dot, electrons are hopping to the catalyst, but all the holes get stuck on the linker, the anchoring group. So once she changed her strategy of synthesis, this quantum dot, she got better efficiency. And again, all the acknowledgement was for the ultra-fast spectroscopy. So based on that, what I want to tell you now, in order to achieve robust, stable, and efficient solar fuel systems, we need to overcome some bottlenecks. First one, the optimal distance between the light absorber and the catalyst. It needs to be optimal. It doesn't need to be short or long. If it's so short, after injection, there will be a combination back. So you lost the charge again. If it's too long, you might have trap states that trap the charge. So it needs to be optimal. You need to have a robust skeleton. And we heard a lot yesterday about MOF and COF. And both are really strong because they show high thermal stability, high photostability. So they are stable, high chemical stability. So you need something that's really robust. And you need to have a broad absorptivity because the visible spectrum is wide. You can't just pick up only one wavelength. You need to pick up as much as you can. And you need the very important one, you need to fill in the time gap. What does it mean? Light interaction with the matter is very fast. It's femtosecond to picosecond time scale. While most of the catalytic reactions or the electron harvesting or Hall harvesting are millisecond time scale. So there is time gap. You need to fill that by having, for example, a material work as electron store to hold the charge for some time until the catalyst is ready. And finally, most of the catalytic reaction are multi-electron hole pairs. So you need to have charge accumulation. So all these bottlenecks now, if you take them, you will get something very useful. And I see MOF and COF doing a great job in this particular point. Because what we saw yesterday, you can engineer them with high precision. So if you manage to put light absorber, catalyst, certain distance, and you apply photo, you will get higher efficiency. And this was one of examples. We used COF actually, where we have this COF from these materials, by pyridine as well, and we decorate them with rhenium. Why rhenium? Because it's well known for CO2 reduction. And we got that. We managed to investigate what we call it the black box. What's the black box? We don't know unless you do spectroscopy. So all the solid arrows means what we need. Favorable process. Excitation, injection, reduction, done. But other dashed arrows mean that you are wasting energy, wasting charges. And we managed to study all of that in very good details, and it's published already. And recently, actually, also in my group in United Arab Emirates University, we used some simple COF actually based on Lansana materials in order to do some thermocatalytic reactions, where, for example, we managed to acetylize the benzaldehyde to dimethoxymethyl benzene, as well as our MOF shows a beautiful light activity, as you can see in this video now. Once you shine them by light, UV light, you get this kind of beautiful. So now we are working how we can do that photochemically. And we did already some preliminary results that I hope I can share it with you next time. Not only that, actually, with the collaboration with Professor Cornelius Kleiner in Goethe University, my postdoc, she visited their lab for a month within research mobility, actually, and she studied magnetic properties for magnetic device for data storage. MOF, again. And by the way, this is simple MOF. This is not as complicated as what we heard from Dr. Dawoodi and Dr. Omar. They are very simple. But look at the application. It's a very beautiful application. And now, what I am doing in United Arab Emirates University, actually, as I told you, I started there 2 years ago, which is not really long time. But actually, we are doing great. So I have now a small group, but we are big in the impact, actually. So we are using MOF and COF for different applications, catalytic application, thermally or photo catalytic applications. Also, I am back now to the quantum dot field again, maybe not for solar cell, but for LED, for photo and electrocatalytic reactions, as well as with these great people, actually. We are working with some environmentally friendly quantum dot. We make them in a sustainable way to use them as a drug delivery, and this is really our target in the next few years. Take-home message. Spectroscopy, simply, it tells you or helps you to discover what's happening once your light and matter interact. Once they interact, there is a lot of information, hidden information we don't see. If we learn what's happening actually, we can work to modify, enhance their performance. It's very important to understand different materials, any light-active materials, and I recommend that we keep attention how we consume energy, because this will come back to us soon. And spectroscopy is always awesome and fun, but you need just to understand what you are doing. And maybe it's too big a slide to acknowledge all these people, but I would like to thank my former groups in Lund and Uppsala as well, and also my collaborator in Germany, Dr. Christine, for hosting my postdoc, Dr. Reem, for a month there. This is my X-ray team that I brought from, and of course, Professor Saleh, Professor Osama, Professor Naila, for their collaboration. And this is my team that they are all here now, my undergrad students and my postdoc. And yes, of course, very big acknowledgement for my collaborators and also for AGIA, since I am a steering committee AGIA member, Arab-German Young Academy for Science and Humanities. Of course, the support from the Research Office in United Arab Emirates, my grants. And now, if you want to join this beautiful family, I have a postdoc announcement or RA that if you are interested, you are very welcome to send me your CV. And thank you so much.
Thank you, Dr. Qenawy, for the nice presentation. Now we have maybe 2 or 3 questions. Please.
Very wonderful talk. Just wanted to ask that in your lanthanide MOF, the europium and terbium are the metal center, or you have integrated it post-synthetically?
No, they are the metal centers.
And can you just tell me what is the ligand for that?
It was oxalic acid, or oxalate, yes.
Oxalate,
Yeah.
okay.
For this particular one, and we have another ligand. We have BTC as well.
Yes. I understood.
Yes.
Yeah, thank you.
No problem.
Other questions?
Thank you very much. It's fascinating to see how you're building up your team here. This is a non-technical question.
Okay.
But what are the sources of research funding for you in UAEU, and how do you become competitive in a fast-moving world?
Yeah, actually, it is, honestly, there is, I would say, generous grants you can apply for, but it's always competitive. So, for example, since I joined United Arab Emirates University, which is 2 years, I'm lucky I got 2 big grants. When I say big, relatively big, because you can't say really how big it is. And small grant, two small grants. So there is grants, you need to apply, and it's examined internally first, then externally. And then you get, based on the feedback from the external reviewers, actually, you get to know if you are awarded or not. So it is, there is grants, yes.
And are these federal grants, or are
No,
they?
They are from the university. I don't know if is it federal or not. It is.
So there's no federal funding system in, like, the National Science Foundation? Yeah.
Unfortunately.
Yeah. Let's try and change that.
Please.
Okay, thank you.
Pleasure. Come on, more questions.
Other questions from the audience? Okay, please join me to thank Dr. Qenawy again.